to part 3 of Electrochem Diploma and Test Prep. We're now into the Electrochem application section, and this video will go through the first half of the application general outcomes. We've already in part 1 and 2 gone through general outcome 1, which has a lot of the important intro terms of electrochem, like oxidation, reduction, OAs, and RAs. We're now in general outcome 2, which really focuses on voltaic and electrolytic cells. We're going to go through the first 4 outcomes in this video, focusing on things like anode, cathode, salt bridge, ion movement, internal and external cell, internal circuit, of both voltaic and electrolytic cells. We'll compare the similarities and differences, and I'll summarize them in a color-coded slide. We'll look at the reactions that occur at both electrodes in our electrochemical cells, and look at one example where our table doesn't make the correct prediction for the chemistry that will occur. So general outcome 2, we'll start with defining the anode, cathode. We'll talk about ion movement more in the next slide. In this slide will really get into kind of the salt bridge force cup, the need for electrolytes both in the salt bridge and in our beakers, internal and external cell, power and power supply are 2 types of circuits. We'll focus more on the similarities and differences in a future slide, but they're definitely going to come up here. On the left, we have what's labeled as an electrochemical cell, but it is the voltaic kind. And we see 2 beakers, 2 different solutions, and 2 different half reactions occur in each beaker. One thing you definitely need is to have electrolytes both as your solutions in each beaker or half cell, and you need to have an electrolyte of salt in your U-shaped tube or salt bridge. If the salt bridge has a molecule, then the cathode and ions can move the anode, and your cell will want to build up a charge and it just will not operate. One thing I've seen in the past is putting a molecule in replace of a salt. So if you saw something like CH3OH, a alcohol, methanol, that wouldn't allow the cell to run. Now in the cell, I'm just going to label the anode and cathode. We'll talk with the terming later. The cathode in this example is on the left, and the anode is on the right, and that's not a rule. You just have to figure it out based on the chemistry that's occurring. Now I'm a big Leo and Gerd teacher, so gaining electrons reduce, and reduction is always what happens at the cathode. Our anode is where we're losing electrons for oxidation. Now, electrons are negative and they're lost at the anode, so that makes the anode negative. The electrons are coming from that side. So we have our electrons flowing through our external circuit to the cathode, which is going to be our positive electrode. So negative electrons are flowing from the negative to the positive. Now this flow of electrons has to be balanced by some ion movement to keep the cell neutral. So any positive ions, any cations, are going to be flowing towards the cathode. So I always remember C or constant. Now it's going to be the potassium in this example that's in the salt, but any positive ion is going to move. Negative ions, like the nitrate, are going to be moving towards the anode. Then this is just a balanced charge. So as you lose electrons at the anode, we'll get some negative charge to balance it. Every mole of electrons that is lost will have like a mole of negative charge coming back to replace it. So we've covered a lot of the terms. We'll dive into them more. We've got anode and cathode and their polarity. We've got cation and anion movement. We have a salt bridge. We haven't come across a porous cup yet. We will at the bottom of the slide. And we need to have electrolytes that have ions throughout our cell. Now, our external cell is the wires that connect the anode and the cathode. power supply listed, but that doesn't change the labeling of the external cell. Now, in a electrolytic external cell, you need to have a power supply or a battery that's going to run that cell. And you're just going to have one electrolyte solution in a electrolytic cell. So maybe you have a aqueous potassium iodide solution. And you're not going to have two different solutions. And you're going to have your two electrodes right into that same solution. Now you're going to have a cathode and an anode. I've labeled these. They're not actually determined yet. What makes one side the cathode and one side the anode is going to be your power supply. Now, one big difference is the polarity. Your cathode is actually going to be negative in a electrolytic cell, and the anode is positive. Now, it's not the LEO at the anode that's causing the electrons to move. The anode is still losing electrons, but they don't really want to go out of the anode. It's a non-spontaneous cell. You need the positive terminal, the power supply, to be at the anode, ripping those electrons out where they don't want to leave. The other side, the negative side of a power supply, is going to force electrons out of the cathode. So I'm labeling everything on the right-hand side is negative, the negative terminal of our power supply or battery, all the way over to our negative cathode. We're forcing electrons there, ripping them out of the anode. So we've got the same electron movement from anode to cathode. It's just what's driving it. It's kind of like we're going uphill against gravity, and the power supply forces that. Now, one type of diagram that could confuse students is if you have a porous cup. That makes a voltaic cell kind of look electrolytic. Now, a porous cup is just a cup, but it's made out of a ceramic, and ions can flow through it. Solutions, water, solvents can flow through it, but if you have a gradient, a pull to try to get positive charge to go to one of the electrodes, they will flow right through. So we could have a copper gold voltaic cell, and it could all be one beaker. We could have our copper 2+ ions inside and have a elemental copper electrode. And that's the inside a beaker, and that beaker will have elemental gold as its electrode and gold ions around that electrode. And this is going to be a voltaic cell now. We've got two different electrolytes. It's important that the gold solution doesn't overtop the porous cup, so the copper ions and the gold ions are kept totally separate. And if you connect up those two electrodes with a wire, an external cell, current is going to flow from the anode to the cathode. And cations and anions can flow right through that porous cup and get to the appropriate electrode. Cations move towards the cathode, anions move towards the anode. And you would have anions both inside the porous cup and outside, and any of those anions would move towards the anode. In this case, the copper is the lower down of the two half reactions. Cations from anywhere, the gold ions, the copper ions will want to migrate towards the cathode. So we've covered a fair bit of these outcomes. We're going to sort of repeat these a little bit as well as bring in the half reactions. So we're still kind of on the same two outcomes, B2.1, B2.3, and I am jumping ahead to the third one now. So we have a tin ion, tin metal, a half cell on the left, and we have silver, labeling some loss, and silver metal, silver ions on the right. And to predict the chemistry that's going to happen in the cell, you don't have to use multi-step methods and make big lists. You can just grab the chemistry right from your table. I have underlined the two half reactions that are occurring in yellow. The higher up half reaction is going to have the best oxidizing agent. The strongest oxidizing agent will come from the top half reaction. The lower down half reaction will give us our strongest reducing agent. And we can just grab these two half reactions from our beaker, from our table, and we'll know what's happening in our beakers and do some labeling. So the best OA, which is going to react at the cathode, we can just pull that right from our table because that's a reduction. So we're going to have silver plus aqueous plus 1 electron, making elemental silver. You know, the strongest reducing agent that's going to occur at the anode, we've got to flip that from our table because we need to write oxidation. Nickel solid to nickel. Sorry, my line's a little low. It's the tin, not the nickel. Quickly fix that. Sorry about my yellow line being a little bit low. It's elemental tin, going to tin 2 plus, and spitting out 2 electrons. So that lets us know what's going on chemistry-wise. So our tin is our strongest reducing agent. That's our anode. So our anode happens to be on the left in this example, and it's a voltaic cell, so it's going to be negative. Our higher up half reaction, our silver one, is going to be our cathode, it's going to be positive. So in our external cell, the electrons are going to flow from the anode to cathode. This lets us know our ion movement is going to be flowing. The cations are going to go towards the cathode. So something like potassium plus is going to be flowing towards our cathode. Our nitrate, a little hidden NO3 minus, is going to be moving towards our anode. Again, the point of this is to keep neutral solutions. Any corrupt charge will prevent our chemistry from running. We can do the same thing with electrolytic cells. So an unlabeled cell down on the bottom, and I'm going to draw a potassium iodide cell, a potential lab that you might have done. So now we have one solution. We have some iodide, and I'm going to use 2 inert electrodes. Carbon and platinum PT are the 2 inert or non-reactive electrodes you should be familiar with in chemistry 30. Now, unfortunately, when you get to electrolytic cells, you've got to spend a little bit more time. I would hope that a voltaic cell, you go to your data vault way, you answer them really quickly. But in electrolytic, you've got to make a list of everything present and find your 2 best species. So that potassium iodide, we have to break it up with building our list. We don't have ionic compounds on our reduction table with individual cations and ions or elemental species. We've got potassium ions in solution. We've got iodide ions, and it's aqueous, so we have to include water, solvent. I like to label OAs on the top and RAs on the bottom, and then I can find our winners. All metal ions are OAs. Iodide is on the RA on the right-hand side of our table. Water is in both columns. Water can potentially be an OA or an RA. Of the 2 OAs, we have 2 really poor ones. We have potassium way at the bottom, and water is still pretty low, but slightly better. So the strongest oxidizing agent that we have is water. Not great, but the best we have. So the SOA, which will occur by cathode, so the 2 waters, the solvent, plus 2 electrons, hydrogen gas, and 2 hydroxide ions. We're just grabbing that right from the table. In terms of reducing agents, we've got water, but RA water versus iodide. So it's the way on our table, you've got iodide there, and you've got water above it. Now, as we go up, we get stronger oxidizing agents, but as we go down, we get stronger reducing agents. So the iodide is better than water. So procedure is really the same for dealing with Voltaic and Electrolytic, other than you need to make the list and find the winners as opposed to just identifying them quickly from the table. So I'm grabbing the half reaction from the table, but I'm flipping it because I want the oxidation. Now your table lists iodine and solid. Yeah, a little bit of it will dissolve. If you run this lab, you've probably seen a brown iodine solution. If you collect the iodine, purify it, you'll have a nice purple color. This now kind of sets what's going to happen. We're going to need a power supply. You're going to connect it up. You're going to have to make one side positive, one side negative. And that's going to set which is which. So the positive side would be our anode, and the negative side would be our cathode. And so our chemistry tells us at our cathode, we're going to get hydrogen gas produced. So we're going to get bubbles coming off. And if we do a litmus test, we will be able to pick up the hydroxide ions. At the anode is where you're going to get that I2 coming off, which in real life is brown, but collected again, iodine and purple. So that's some of the equation writing and talking about terms in Voltaic and Electrolytic cells. I guess last I'll just add in ion flow to this. Our iodide is acting as a chemical that reacts, but it's also an ion that's going to move. And I'll just label generically, we're going to have any positive ions in solution going to the cathode, so that would be our potassium plus, and we're going to have iodide ions moving towards the anode, hope to balance charge and act as a reactant there to make the I2. So moving to sort of wrap things up, comparing the similarity differences between Voltaic and Electrolytic cells. This is kind of a summary down below that I give my students, and I color code anything in red that changes between the Voltaic and Electrolytic cell. So spontaneity changes, cell potential changes. It's always the OA at the cathode, so I leave that in black, but the polarity of the electrode switches. So cathode is always the OA, the anode is always the RA. Now at the bottom, nothing changes, it's all black. The electron flow is always anode to cathode, and the ion flow, which is in solution, make sure you don't label this in the external part of the cell, is anode, anions to anode, so I remember vowel to vowel, and cations always move towards the cathode, so constant to constant. Now the electron flow is always in the external cell, where the ion flow is inside your cell. So at the top is an old diploma question. About the similarities and differences. So which row identifies a characteristic of each type of cell? So the table below helps us. Definitely expect a question like this in your diploma. Eon cells less than 0, that is not true for a Voltaic cell. It's kind of switched in row A, they switched the two statements, they should be with the other cells. E converts chemical energy to electrical energy. That looks good, and moves anions towards the cathode. That's backwards. Cations for the cathode, anions for the anode. So the ion flow is correct, so B doesn't work. C moves electrons towards the anode. No, they flow from the anode. So that one doesn't look good. The bottom one requires a type of salt bridge, mostly true, of course, how to replace that, and requires an external power supply. That works. So this is how you're going to get tested on the similarities and differences. They could ask you for similarity or difference, including drawings. Last bit is that we'll go through. I've already done lots of stuff writing the equations, so I'm going to skip that. It's talking about an exception. There are many times when the table doesn't make the exact right prediction, and you just need to know about the production of chlorine gas. So I've got an example that we'll work through. An electrolytic cell is constructed with aqueous sodium chloride and hydrochloric acid. And what product is produced at the anode? So this is an electrolytic cell, so you need to make a list and find your two winners. So I'm going to start with aqueous sodium chloride. I'm going to break that up. So we've got sodium ions, chloride ions, hydrochloric acid. That is a strong acid, which would 100% ionize. So I'm going to break that up to H plus and Cl minus. Now I already have chloride on my lips, so I'm not going to repeat it. But last I have to add water. Now I always like to add water at the end. It's just how I do things and make sure I never forget to solve it. Then we have to list the OAs and the RAs. All metal ions are OAs, sometimes they're both. Sodium is a OA in this case. Chloride is a reducing agent. H plus is an oxidizing agent. Water can potentially be both. And we've got this pairing. We've got chloride and water together are a potential oxidizing agent. Sorry, reducing agent. So that completes our labeling. Now the chloride anomaly just focuses on RAs, which are out the bottom. When you have chloride and water, our table says water should be the winner, but it is not correct. It's not what we see. What we actually see is chloride reacting. So this question is the chloride anomaly. In Chem 30, you need to correctly identify chloride as what's going to react, not water. If there are any other RAs below water, well then they would be the winner. In terms of OAs, there is no effect with the chloride anomaly. Just find the best OA as normal. So these three reducing agents, we're going to use the anomalous chloride. For OAs, H plus is the best oxidizing agent. We've got H plus, which is our winner. We've water down below. We've got sodium ions even lower. So we know our chemistry, we can pretty much answer the question. The best oxidizing agent at the cathode is going to be the H plus half reaction, one you should have seen a lot throughout this course. To get to this question, we need the best reducing agent that occurs at the anode. And this is the oxidation, so the flip of the equation that's in the table. 2 chloride ions is going to make elemental chlorine. So what is the product produced at the anode? Is going to be elemental chlorine or chlorine gas, which is bubble. So that concludes the first half of the cell applications, and we'll dive into those last few outcomes in the last and fourth video of this series.